a straight line, but they are different. They could be moving in different directions, but we're going to choose to align them when we look at relativistic phenomena. We are also experts in simultaneity. We know that as you get close to the speed of light, what might be simultaneous to somebody in this frame is not necessarily simultaneous to somebody in this frame. And neither of them are wrong, they're both correct. So in relativistic terms, you can have two answers to the same question. Just for your information, I've got worked examples of 4 different phenomena. One is time dilation, one is length contraction, there's another one about time dilation, and you, after the lectures, if you would like to take a copy, if you want to study further, please have a look at it. It explains it gives you worked examples of what we are actually doing in these lectures. There is a video recording being made of these lectures, and within the next 3 weeks, probably the end of the month, they'll be available on the UCT website. I believe as well tomorrow afternoon at 3:15 there's a film on special relativity. It's obviously a video from, I think it's from YouTube somewhere. Have a look at the film program. It's free for anybody to go, so that will be good. When they put the videos up, I'm going to send UCT the links to a whole lot of other YouTube videos that you might want to look at in due course. There are quite a lot of good ones, and there are also quite a few bad ones, and I'll give you the links to the better ones. All right, let's get started then. This is the problem I posed to you yesterday. This is a special case where light can travel through the Earth, and you can see the signal from Johannesburg and Cape Town when you're in DR. And South African Railways has got trains that can travel at 99% of the speed of light. So let me do, which of the answers is correct? Who says A is the correct answer? Put their hands up. 1, 2, 3, 4. Okay. B and C. Okay, well, C is the correct answer. Remember, what's happening here is that Motsi is moving towards Johannesburg. The light beam from Johannesburg is coming towards her. So she's going to bump into that wavefront first. The one from Cape Town is going to take time to catch up with her. So she'll know that it's noon in DR. She'll think it's afternoon in Johannesburg because it's past, and it's still morning in Cape Town because the 12 noon signal hasn't reached her. But when it does, and it's a case of, again, of simultaneity. All 3 of these clocks, remember Jan was a clever guy and he actually got them all synchronized. They were all telling the same time, but when she looked at them, she got 3 different times. All right. Yes?
What do you think, if the train stops in Johannesburg, it's had to decelerate? What do you think of that?
But he's not, well, this is going flat out into, I'm going to come to something that acceleration can affect. To be quite honest, in special relativity, the best thing is to ignore acceleration and deacceleration because it isn't a major part. It only affects time at the very end of the journey. But when the trains stop at the end, all the clocks come together again because now they've all moved into the same reference frame. They've actually jumped reference frames. You've gone from a moving one to a stationary one, and then things are different. Okay.
So A is right.
Sorry?
The train stops, so A is right.
If the train stops, yes. But they're in DR. Halfway there. Okay. Let me move on from there. Here's another one. I'm going to let you read it. It's a question about a rocket ship flying past Earth, and it sends out a flashlight. The question is, what shape will the light front from that torch, from that light, the flash that's been emitted, take on? Will it be circular or will it be elliptical? It's going to be circular. Now, the reason for that is, as we said before, that the speed of light is constant in all directions. It doesn't matter who's moving, what's moving, it's the same. So from that point where the light starts, it will radiate out equal quantities in all directions. So it can't be elliptical. The next question then is it centered on the rocket or is it centered somewhere else? Well, it's centered somewhere else, because by the time you see it, that rocket has moved on, but the light source, the position at which that light was emitted, hasn't changed. So there's a sphere of light radiating outwards from that point, and now that the rocket has moved on, it's got nothing to do with it anymore. That rocket is history to the thing, okay? Silence, okay.
I think a good analogy is if you're watching an aircraft flying by at high speed.
Yes.
You can see that aircraft is there, but the sound's still coming from.
Well, that's, yes. Well, but you're mixing sound and yes. You know. Okay. All right. The next subject we're going to look at is time dilation and Lorentz gamma, and this is where we start to get into the meat of special relativity, and there will be more maths today than yesterday, because yesterday there was virtually no maths. But in order to get a better understanding of what I showed you, we need to get a better understanding of what's happening between different frames of reference. I'm going to do this using another thought experiment, and the objective of the experiment is to show that observers measure any clock to run slow if it moves relative to them, and as the relative speed approaches the speed of light, the moving clock's change in time tends to 0. So if I were to take off in a rocket ship from here and move away ultimately at the speed of light, the observer on Earth would see the time in my rocket ship stationary. The person in the rocket ship wouldn't see a change in time, but the person on Earth would. A way of thinking about it is, if you were to hop onto a photon and travel with it, it'll never change time, because that photon of time goes with you, and you can't see in front of you and you can't see behind you. So you can't see the future, you can't see the past, you can only see the present. In other words, time stops. It's perhaps a simpler way of thinking about it. All right, I've got my train set up there, and I'm going to imagine that this train is moving close to the speed of light along a straight stretch of railway track. Sarah's sitting in the coach, here she is. And Sarah is sitting here halfway between, in fact, for this, it doesn't matter that Sarah's near the back or the front. And what Sarah's got with her is a light clock. And all that is she takes a light source and a mirror. This would be at the roof of the carriage, and she will shine a light. Let me get it. There you are. Can you see it on the table? And what Sarah's going to do is measure the time that the light beam takes to go there and back. So that it's going to go up, reflect there, come down. And she's got a very, very accurate stopwatch with her, and she can measure what the length of time is. Now, to Sarah, if she was blindfolded or if she was inside a carriage that was completely dark, she would not know that she's moving. As far as she is concerned, the light, even while this lot is moving relative to us, the light and the light source, they just go backwards and forwards, up and down. Okay? You all got that? So she could just as well, me standing here and doing the experiment stationary, it's the same as her doing it on that moving train, because she's in an inertial reference frame going at a constant speed. However, a second observer, Peter, that is over here, won't observe the same as she does. When she shines the light to go up to the ceiling, he'll see the light leaving her, But now the train's going to move along, and remember, it's moving virtually at the speed of light. He's going to see a light beam that comes up here, reflects off the mirror when it's here, and sees it strike the ground again when the train is there. So from Sarah's point of view, the light beam's going up and down. From Peter's point of view, the light beam's going like that, and then like that. And it's patently obvious that the light beam that's going this way is traveling a longer distance than the one that's just going up and down. Okay, let me just get back to the slides. Because from that, we're going to determine how time changes as your relative speed changes. Here's the example. On the left, we have Sarah. Let me just get my pointer. And on the right, in the center of the slide, we've got Peter. But this is Sarah here, and she's measuring the distance that the light beam has to travel in her frame of reference is d. And in Peter's frame of reference, it's got to go up there and down there. In other words, it's got to travel a distance of L plus L, which is 2L. Just to reiterate, the first event occurs here where Sarah turns on the light. And but the event 2 occurs at the same position because the light goes up and the light comes down. And this is what we mean by a light clock. Now, Sarah measures a round trip, which I've called delta T naught for the light beam. So that's the amount of time it takes to go up and down. And that is called proper time. Wherever you see delta T naught, or a tau sometimes, it means proper time. And what is proper time? Proper time is the time read on a clock that is present at all events. In Sarah's case, she would have to take a clock with her on the train to measure the two events. But that same clock there would measure, let me just pull it this way, would measure the time that she sets the light off, and again over there. Whereas Peter on the ground is going to need 2 clocks to measure the difference. He can't have 1 clock in 2 places, but Sarah can move with her clock. Now the light beam travels a distance of 2d, whereas that is there, that's quite obvious, in a time of delta t. And we know that the speed of light is constant c. So we can work out d in terms of delta t, and that's c delta t over 2. It's a simple, it's not a difficult piece of mathematics. That is time times time, speed times time equals distance, okay? Let's see what Peter sees. He sees the first event taking place here. The light has to then move up there and come back there. But in that time, the source has moved from O prime over there to O prime over there. It's no longer in the same location as it was in Sarah's case. So he's got a diagonal path. And as I've said, event 2 occurs over there. So that's what Peter's going to measure. And he measures the round trip time to be delta t. We don't know what delta t is at this moment, but you can guess already delta t is going to be bigger than delta t naught, because that beam of light's got to travel a lot further, and it's traveling at the speed of light. And if it's got to travel further, it's going to take longer. The distance traveled in that time is simple. The train's moving at speed u, which I said is about 99% the speed of light. And the distance covered will be u delta t. All right? Distance is speed times time. Now, sorry. Yeah.
So if we look at that vertical line,
Yes.
inside the cavity,
Yes.
a single photon leaves the mirror.
Yes.
Both the mirror and the source are moving that.
Yes.
The photon has now been released.
Yes.
Why does it also move laterally at the same speed?
Be- Because it's in an inertial reference frame. If it was in an accelerating frame, it wouldn't do it.
I understand that, but it's not like a complete answer. When I understand it, something missing in it. I don't see why it should not, in fact, come to the bottom of the train a little bit further back than the point of its aiming train.
No, yeah. Dave, I'll discuss it with you afterwards, okay. Well, maybe once you see more of the maths, it'll become clearer, or less clear. All right. All right. Just a reminder of, let me just go back here quickly. You can see what we've got here is a triangle. If we drop a vertical down here, we'll have a triangle with height d over there and u delta t over 2 over here. And from that, we can actually compute what L is in terms of L and U delta T. But to do that, I just need to remind you of Pythagoras' theorem. And if you, this is even before metric geometry, I hope. But if you remember, c squared equals a squared plus b squared. There's the equation over there. And therefore, c equals a squared plus b squared, the square root of it. Okay? So how could we apply that to the example that I've just given you? Here is the triangle with the sides L and L. You drop d down at the right angle there. That distance becomes u delta t over 2 because this point here will be halfway between the two O's. And there we are. We have it. L is equal to d squared plus u delta t over 2 squared and the square root of all of that. Have I lost you, or are you able to keep up with that? All right. But the speed of light is the same for both observers. And this is where, you know, it starts to confuse people. But it is the same. So the round trip time measured in S is delta t, where delta t is equal to 2L over c. There's L over there. If I plug in L into the equation, then you get delta t is equal to 2c over that square root sign there. Stop me if I'm getting it wrong, or if you would like more of an explanation. But what we would like is a relationship between delta t and delta t naught that is independent of d, but is dependent on u and c. Now remember that d is equal to c delta t over 2, delta t naught. Then by substitution, we get this equation here. It's the same square root, it's just got a few more variables thrown in. But that equation there can be simplified. If you square it and then solve for delta t, you get this equation here. Delta t is equal to delta t naught over the square root of 1 minus u squared over c squared. And that is the time dilation equation. Now what you can see immediately just by examination is that u can never be greater than c. So, but it can be equal to c, and at the extreme, when u gets up to the speed of light, you've got 1 minus 1, and that's 0. If you divide anything by 0, you get an infinite answer, and this whole equation is nonsense, which is mathematically one of the reasons why you cannot go faster than the speed of light. And indeed, if you could go, let's supposing u was slightly bigger than c, then this would be a negative number here. And now time would become the square root of a negative number, which is an imaginary number. And time is not imaginary, it's real. So there'll be more and more evidence like this coming through why you can't do it. So when people say they've come up with a method, well, either Pythagoras is wrong or something else is just doesn't make sense. This is almost proof of Pythagoras' theorem, that's as one person has put it to me. All right, since that quantity, the square root of 1 minus u squared over c is always less than 1, delta t is always greater than delta t naught. In other words, the proper time is always less than the time measured by an observer in a different reference frame. And thus Peter measures a longer round trip than does Sarah. This quantity of 1 over the square root of 1 minus u over c squared appears in most relativistic equations when you're doing the work, and it's referred to as Lorentz gamma. That's the sign that we use, just to make it simple. But if you work with this every day, you don't write out this big equation, you just use that symbol in doing your analysis. And there we are, there's the Lorentz gamma factor. I've given you a sheet with all the important equations on it, and this is one of them that is there. It is absolutely fundamental to understanding all of the other stuff. We're going to be using gamma quite a lot further on into the lecture. Note that gamma is always greater than or equal to 1, and 1 over gamma is always less than or equal to 1. And this is quite a useful thing. If gamma appears in the numerator of any relativistic equation, it will tend towards infinity as velocity u approaches c. Conversely, if gamma appears in the denominator of an equation, then as u over c approaches 1, gamma tends to 0. So you'll know straight away when you look at an equation, if the gamma is in the numerator or the denominator, you can tell which way the equation is going to tend to. Delta t naught is called the proper time, and it's equal to the time between two events that occur at the same position. So just getting back to this one again, remember, although she's moving, her frame of reference, her reference frame, she's stationary in her reference frame, and therefore the signal just goes straight up and down. And she's got the clock present at both locations, both where the light went up, and again where the light came down. Only one inertial frame, and usually we'll use the S prime frame, measures the proper time. Again, it's just reiterating the point I've made. An inertial reference frame moving with velocity u relative to the proper time frame must use 2 clocks to measure the interval, like I've illustrated over there. One at the first event and one at the second event. Now, by rearranging our earlier equations, we can, the time interval in the frame where the 2 clocks are required is as follows, where delta t equals delta t naught divided by that, which is gamma delta t naught. And thus delta t is greater than delta t naught. Remember Peter over there, he was measuring the time that signal took to go up and down. He measures a longer time than Sarah does. And the stretching out of time is called time dilation. That's all that happens. And we're beginning to get a gentle introduction that we are swapping space and time with each other. Yes?
Okay, what I don't understand about this is Sarah's only moving in reference to Peter. Peter's also moving in reference to Sarah.
Yes.
So it seems like if he were moving the light up and down, just the opposite would happen, and so you get the opposite effect.
You're absolutely correct. If we did it the other way around, if Peter was the one shining the torch and Sarah was the one moving, yeah. And this is the problem with relativity. Both are correct. Both will say each other's clock's running slower, and they're both right. Okay. Not a misunderstanding. It's very good. Did you all get that? It's an important point. I think the problem we have is that we think we are in a stationary reference frame, but we are moving at a hell of a lick at the moment. And photons that go up to the roof, Dave, and come back down again, they're not moving sideways either. It's living proof that, that's coming straight back at me. It's not going over there.
So then how much time went by just ends up which reference frame they both end up?
Yes. One of the problems with this is how does she communicate what she's picked up? She'd have to write it down. They'd each have to write down times and afterwards compare notes. I'm going to do a little experiment where we're going to do that. Okay.
Sorry, if I may comment
Mm.
on the last point. I've read several books in which a situation is described where brothers, one of whom remains on the earth and the other one goes on some sort of...
Yes.
When he comes back, he's 20 years older or younger than his other brother.
And that,
They're not both 20 years older.
okay. There's a good reason for that, and it's because of symmetry breaking, which I'm not going to cover today, but tomorrow I will, because you need another set of equations called the Lorentz transforms, where you can work it out. But yes, it is true, the traveling twin comes back younger. But I'll explain in words tomorrow. There's a very good YouTube video. I don't think we'll have time to show it here, but I'll give you the reference where you get the full explanation of how it happens. Okay? But it does, you can make the time change permanent, but that needs further explanation. I'll need to go through a little bit more of what we're talking about here. Okay, the equation by itself has two things. It's not possible to go faster than the speed of light, etc. I've told you that already. If we plot delta t over delta t naught as a function relative to as a function of relative velocity, it'll tend to infinity. The graph will go up. And this is the bit, if you've not understood the maths, don't worry. This is the useful bit that comes out of what I've said so far. What you've got on the bottom axis here is your speed relative to the speed of light. You start off stationary, which is 0, and it goes to 1 as you hit the speed of light, because you're just looking at the ratio over there. As that happens, your delta t over delta t naught, remember delta t is the time measured by that guy there, and delta t naught is measured by her. That equals gamma, and gamma is going to go screaming off to infinity, which is what it does. You'll notice that up to about 20% of the speed of light, the line is pretty flat. And up to those speeds, Newton's laws are perfectly valid. Where Newton's laws start to fall down is when you get up to these higher speeds, because he would just simply say it would continue straight along that line. But no, the times really do start to change. As I've said, the one way to think about it is if you were traveling with a photon, time would stop, because that photon's time is never going to change. And then you would be traveling at the speed of light. So if you could hop onto a photon and go with it, then you would know that.
If you were on a photon and you left the sun, at the same moment you would arrive on the Earth.
No. It takes 8 minutes for a photon to get to the Earth.
8 minutes?
Yes, yeah.
Not for a photon.
Yes, 8 minutes for a photon. 60 minutes to Mars, 2 seconds to the moon, and it just gets bigger and bigger the further you go. Yeah.
I think she was saying in terms of the photon's time difference.
No, the photon's time won't change at all. It'll arrive at the same time that it left the sun. Yes. Okay.
So in the photon's frame.
Yes, in the photon's frame of reference. Oh, okay. Yeah. Yes.
Hi, over here. So, can you see me?
Yes.
So does that mean that if time stops, as you approach, or tends to
Yeah.
dilate infinitely, right?
Yeah.
Does that mean that any organism
Yeah. Yes.
Time stops, but does
Yes.
physical activity stop? Does biological...
Well, okay. Okay. If you got to 99.999999%, but not quite there, nothing stops. It just slows down. I've got a good question for the medical guys here later on. What happens to your ECG when you're in one of those rockets? I hope they can tell me. Okay, were there any other questions? Yes, sir. Yes. You got a question? No? Yes?
Regarding the twin paradox, I thought you needed general relativity.
No.
An accelerating body there.
That's science fiction, I'm afraid, not science fact. And one of the things I'm hoping to do in these lectures is to give you the facts and try and steer you away from some of them. There are all sorts of things that over the years have been wrongly interpreted. It's not because of general relativity, but it's easily to be fooled into believing it is that. And you get lots of videos that tell you that. You have other things. People believe your mass gets bigger as you get to the speed of light. It doesn't. We will come back to that. Okay, I better get a move on. Okay, time dilation, sometimes described by saying that moving clocks run slow. This must be interpreted carefully. The whole point of relativity is that all inertial frames are equally valid, so there's no absolute sense in which a clock is moving or at rest. In the reference frame, you will not know the difference. Okay, this is an example, but I think rather than do it with slides, I'm going to do it with a real experiment. There were 4 people earlier on who agreed they'd come down and help me. Could those 4 people please come down here now, and we'll do an experiment where you can see what happens with time dilation. Going to have to unplug that and that. Okay. Now what I've got here okay, could one of you sit here and another one sit here? Have you got I need to give you, have you got an alarm, stopwatch? Have you got a stopwatch? You want this one? Okay. You 2 guys are going to stand behind them. What we're going to do, when I pass this clock, I'll just put it over there, when it gets to the center of the screen, will you just remember what the second reading is here? It's not running at the moment. This is the clock on a spacecraft, okay? Or on a train moving at the speed of light. So the time on this clock is going to be slower than the time on the other clocks. All right? Come back to that. What I want you guys to do, okay, you've got that. Can you just get it onto the stopwatch? And what I want you to do is to write down the time that thing shows, or just remember the time. Do you want a piece of paper to write it on? I'll give you a piece of paper. No. Because we're going to look at the difference in time on the 2 systems, and it is important that we get it right, otherwise you're going to get crazy answers. Okay. Okay, now start. Can we bring those 2 stopwatches together? Now we're going to start them. All right, I'm going to get one of you. Can you start these 2 simultaneously? Now, here's a good example. This is simultaneous. These 2 stopwatches are being started at exactly the same time. So when I move them apart, they're telling the same time.
Must I get my pen?
No, there's a pen.
I need my pen, sorry.
Okay, you got a pen. Okay, you've got something to write with, have you? Okay, so press the start button for both. We'll just get both of them going. Are they both running?
Yeah.
Well, this one's going to be difficult to read. I wonder whether we shouldn't...
It's changed, yeah.
Oh, has it got it? Oh, it's got digital numbers. Okay. Don't do anything. Just keep it ready. I want you to stop this one when I get past you, and I want you to stop yours when I get past you, and then we'll look at the difference in the two times. Okay. No, okay, I'm going to tell you when to record the time. You record the time as I get past that clock. When I get to that position there, just write down what this is saying. Okay? It's in seconds and hundredths of a second.
Edge there, in the middle?
In the middle. Okay. It doesn't matter exactly. And you're going to do the same. Well, you're going to stop your stopwatch when I get there. When I get here, you're going to stop the stopwatch when I pass there. Or, okay, there. And you're going to write down the time that you see there. Okay? Is it clear enough? Okay, so this is the rocket ship coming along. It's got its own clock running. Let me just get it going. Yeah, okay. As I come past here, we're going to take a reading of the time on the two sets of watches. But remember, this is going to be the proper time because this clock is present at that event and it's also present at that event. Those are the two events we're going to measure. You ready? Yeah. Okay, here we go. Okay, you got your times? Stop your watch. Write the time down. Okay. Can you both give me your times? Who wants to work out the time difference between these two? And who wants to work out the time difference between these two? Tell me how many seconds difference there is. It's gone blank. Got no signal. Oh, there we go. Here we go. Okay, there we go. There's the slow running clock, okay. All right, have you got the two times? What was the time difference on this clock?
We're rounding up with that.
Yeah. So it was 20 seconds the train. The time on was the 20 seconds, yeah.
The time here was 4.2 and 3 minutes, 0.2 naught.
Yeah, that's right, yeah. So this one, it took 4.2 seconds for the faster clock, which was these two guys here. They had a difference of 4.2 seconds, and the others had a difference of how much? 0.2 seconds. 0.2 seconds. So the time registered between year and year is 0.2. And the ratio of those two, is that my clock? It's yours, is it? Is it my phone? Okay. Is 4. Okay. So if we go back to the graph, thank you. Thank you very much. All right. So what you've seen there is a live demonstration. A live demonstration of time dilation. And I'm going to go back a couple of slides. There we go. We'll go back to this slide here. There we go. Now, they found a ratio of 8. If we go, it's right at the top of this chart. Can you see that train there would be moving at something like 99% of the speed of light? I've worked it out. There we go. For a delta T of 8, it's 0.992% the speed of light. That's the kind of difference that you would get. So the person on the train or in the rocket ship the one moving up and down here, they would actually be traveling at 99.2% of the speed of light in order to give you that time difference. Have I confused you, or does it? Okay. All right. There we go. Question is, can we go faster than the speed of light? Well, I've already shown you mathematically that you can't, but there are areas where the speed of light is changing and space is expanding. And when you go for more than 14 billion years out, the actual speed at which space is expanding is greater than the speed of light. And we will never be able to see stars that are more than 14 billion years old, no matter how powerful the telescopes we ever build, because the light is moving away from us faster than it's traveling towards us. But that's a function of the actual space-time, the structure of space changing. This just emphasizes that this is a photograph taken by the Hubble ultra-deep field image, which is 13 billion light years. We'll be able to see a little bit more. I think the first stars only came, about 500 million or so after the Big Bang, and after that we're not going to see anything. Of course, if we wait another billion years, then we'll see a little bit further back in time, but it's a very slow process. In water, muons can travel faster than the speed of light. And that's a muon is a heavy electron. It's not so much that the electron is speeded up. It's the light that is slowed down as it has to get its way through the water molecules. I've actually seen that, and this is a photograph. I had a brief stint at the Atomic Energy Board, and I looked inside their reactor, and you get this Cherenkov light. It's an ultraviolet type of light. And that it's explained by the difference in speed of light and the speed of muons, but that's in water. The cosmic speed limit has not changed. It's just that the speed of light has slowed down.
So, can I clarify? The muons are moving faster than the speed of light in water,
yes,
but not faster than the speed of light in the vacuum.
That's right. Yeah. Okay. Now, the other thing that happens, and this is quite interesting, you speak to astronomers, they pick up some of the supernova explosions by measuring neutrinos first. So you'd say, oh, well, the neutrino has traveled faster than the speed of light. The neutrino is a nearly massless particle, but it isn't zero, so it travels less than the speed of light, yet it gets to Earth before the photons from the explosion, and that is because the photons are bouncing around inside that fireball, and it can take it years to get out. I think the photons from the inside the sun, it's thousands of years it takes for them to actually escape, and it's the same phenomena. So the neutrino comes along and says, hey, look, something has happened, and then they point their telescopes there and have a look at it, which is quite fascinating. But again, it's not because it's traveling faster than the speed of light. It escaped before the light could escape. No, it's purely that's another good one. Gravity can change the frequency of light. It won't change the speed. The absolute fundamental thing with light is it travels at one speed and only one speed wherever you are all the time. Okay. It's a scattering of the photons, and there's an awful lot of scattering. You can imagine inside a supernova, it's a massive body, and it's just that they're bouncing around and they just can't get out. Yep.
Gravity can't change the speed of a photon. How do black holes prevent light from escaping?
When you get to, when you get to black holes, now you're talking about it. You're quite right. Once you get into that realm of physics where the forces are so big, the light cannot escape. Well, I'm not going to go into the black hole theory, but yes, you're absolutely right. But there the gravitational field is so enormous that it eventually grabs hold of the photons and doesn't let them out. but that's within the black hole. Outside the black hole, the light will get back to normal speed. But I'm maybe not the right guy to answer that question anyway. All right? Okay, just remember, we are constantly moving through space-time at the speed of light in a vacuum. We either experience space or time or a mixture of both. It's a philosophical argument. We leave it to you to think about. I've got a few examples of time dilation in nature. Here's one of them. This is an image of an exploding supernova. It's in a distant galaxy, and its brightness decays at a certain rate, but because it is moving away from us at a substantial fraction of the speed of light, it decays more slowly as seen from Earth. And effectively, the supernova is a moving clock that is running slow. It's very useful because it gives us time to examine these things. That supernova's clock is running slow, so we've got lots of time to examine it. And that's purely because it's moving away from us at a substantial percentage of the speed of light. Yes, this is a very interesting one. High-energy cosmic ray protons entering the upper atmosphere react with the nuclei of nitrogen and oxygen, generating pions that then decay into muons, which are heavy electrons, which move at a speed of 0.994 the speed of light. They were first measured in the early 50s, I think, and it was the first confirmation of relativity being real, because all of Einstein's theories right up until the 50s had no way of measuring it. And this was one of the first, because what happens is the half-life of the muon is only 2.2 microseconds. And after 660 meters, half the would have decayed. But at a speed of 0.994, the half-life is as much as 20 microseconds. And in fact, about 25% of the muons created reach the ground. But if there was no time dilation, only 1 in 2 to the power of 20 would reach the Earth. So yeah, we have a live example of where, because the muon is moving so fast, its clock is still running, its half-life in its reference frame is still 2.2 microseconds, but in our reference frame, it's completely different. And I'll tell you something interesting. You can convert this little thing into a muon detector. All you need is a mobile phone with a camera and a strip of black insulation tape, and you put it across the camera. Now you can't take selfies. There's an app you can download from Cosmic Ray. And for other Android phones, there's an equivalent app. You tape up the camera and you just follow the app's instructions. And what it does is it records muon events. And if you take it outside, you'll get one every few hours striking your phone. Quite fascinating, but it's real. That's all that a muon... I actually asked the physics department whether they had a muon detector, and they told me they had something this big and that high. It was a scintillator, and I thought, wow, no, wait a minute, we can't bring that to the lecture. And then I found out through a lecturer at MIT that you can do it with just your mobile phone. I've tried it, and it works quite well. It works better outside because they don't seem to get through the concrete of a building very well. But they are real, and you can measure them. Okay. So why don't we experience time dilation in our everyday lives? We're traveling around the sun at 220,000 meters a second, so that's pretty fast. You'd expect something to be happening. But when you look at the gamma, it's 1.603. So to all intents and purposes, we are in an inertial reference frame. If that gamma were 1.3, physics experiments conducted on the surface of the Earth would start giving you very wrong answers. But fortunately, it's of a very small effect. This is a high-velocity rifle bullet. There are 13 zeros in that lot. So what's it? 1, 2, no, wait a minute, 11, 9, 10, 11. So a high-velocity rifle bullet doesn't come anywhere near relativistic performance. And I did this here, just calculated this yesterday. The bloodhound is supposed to get up to 1,000 miles an hour, and the gamma there will only be 1, 2, 3, that's 12 noughts and a 6. So the clocks on the bloodhound will be okay. All right. A little bit of time dilation in practice. In cathode ray tubes, the electrons that are being fired reach 30% of the speed of light. And when you're designing a cathode ray tube, you have to take the relativistic effects into account. I was completely unaware of this, and I did the research. So right back when the first television sets were being designed, the engineers designing them had to take into account relativistic effects right as far back as then. This is the interesting one, is our GPS system, which is a dual system. You've got a receiver in your hand, and you've got a satellite transmitting at a substantial altitude above Earth, moving very fast. Because of the speed, the clocks on the satellite run slow relative to Earth. But because they're so high, gravity is less, so the clocks run faster. The net effect is that the actual clocks on a satellite run faster than they do on Earth. But it's special relativity battling with general relativity, and general relativity wins out because it speeds the clocks up a little bit. But you have to correct it, because my understanding is if you do not correct the clocks, you'll get an error of, is it 10 meters or 10 kilometers? Yanni, do you know the answer? It's about 10 meters a day, but it doesn't take many days before you don't know where on Earth you are anymore. But there are two relativistic effects, and I'm not going to cover general relativity, but as gravity gets weaker, clocks slow down. That's speed up. Speed up. It's another interesting phenomenon. Okay, but the engineers that design these systems have to take both of those factors into account. Otherwise, the system simply wouldn't work. Okay, I'm going to move on quickly to length contraction, because obviously this is something that is closely related to time dilation. Let me just, I'm not going to go into a lot of maths here. I'm just going to skip to the answers quickly. Obviously, we need a quantitative relationship which describes what's happening in the length domain. And again, we have a thought experiment where we're traveling near to the speed of light on a railway track. Sarah's in the carriage with a reference frame S. And next to her on the seat, she's got a ruler. Okay, so now she's traveling in this thing. We'll call this Sarah. Here we go. And she's going to measure the length of that ruler as she travels. Now, like she has proper time where she is, she has proper length as well. She can go at any speed she likes. The length of the ruler, as far as Sarah is concerned, isn't going to change. But as far as Peter is concerned, it is going to change. I put that illustration up. I'm not going to do the derivation. I'll give you the answer because we did enough maths with the time dilation, but you use the same kind of reasoning to come up with the answer, which is this one. L equals L naught over gamma. Remember I said gamma is going to appear a lot of times, and it really is. And that's the length contraction formula. It looks very similar to the time dilation formula, and indeed it is. So what happens when you're an observer observing a train coming past near the speed of light? You will measure that ruler to shorten and the time to slow down. Again, in special relativity, length L naught is measured in the frame in which the body is at rest, called a proper length. Oh, incidentally, the length's perpendicular to what we're doing here. If you've got a reference frame like this one moving, and we're going down in this x direction, the y-axis and the z-axis in themselves are not accelerating